As we discussed in a previous lecture, we design digital systems to be resistant to noise by abstracting precise voltages to be ones and zeros. Unfortunately, errors still occur during data transmission of many bits, so that one of these bits, or more, might get flipped, so the ones become zeros and the zeros become ones. The more bits we send, the higher chance that one of our bits will get flipped. To understand how we detect and correct these bit flip errors, let's start by discussing a concept called the Hamming distance. The Hamming distance between two code words is the number of bits that are different between two valid code words. The Hamming distance of a code as a whole is the minimum Hamming distance between all code words. Suppose that we want to send just one bit between two components. The Hamming distance between these code words is 1, as only one bit is different between these two code words. Since these two code words are the only words in the code, the distance of the code is also 1. When the Hamming distance of the code is 1, the receiving component can never detect an error, because if a bit flips, the receiving component still receives valid information. Let's change our code so that it still has two code words, but now each code word consists of 2 bits. We would still have our 2 valid code words, but the Hamming distance for this code would be 2 because each code word differs from the other by 2 bits. In this situation, there are 2 potential bit encodings that would be considered invalid. If one bit gets flipped in error, the receiving component would know that an error occurred because the message does not match valid information in the code. However, the receiving component cannot correct the error because the error has an equal Hamming distance from both valid code words. If we add one more bit, we would have 2 valid code words whose Hamming distance would be 3. We would also have 6 invalid code words. In this situation, the receiving component could still detect if an error occurred in one bit, but now, because the erroneous word has a Hamming distance of 1 from one valid code word that is less than the distance of 2 from the other, we can correct the error. Let's add one more valid code word to our code. If we simply add a code word at this vertex, the overall distance of our code is reduced to 1 from 3 because the minimum distance between these 2 code words is 1. It is irrelevant that this code word is distance 2 from this one, or that this code word is distance 3 from that one. Because we cannot detect every 1-bit error, we say that this code can neither detect nor correct 1 bit of error. However, with a better design of our code, we can create a similar code that would be able to encode 3 valid code words that all have a Hamming distance of 2. This code could detect an error in 1 bit, but it could not correct any errors. Hopefully you may have noticed that as we increase the distance of our code, we increase our ability to detect and correct errors. So, how do we intelligently increase the distance between code words so that we can detect and correct more errors? Naively, we could increase the distance by sending a message multiple times. The receiving component would detect the error by simply comparing the 2 sets of bits. This method is effective, but it requires a lot more hardware, becomes expensive very quickly, and increases the odds that we have an error since more bits are being sent. Alternatively, we could require that the transmitting component send an even or odd number of ones in its transmission. In this case, we would simply add one more bit to the transmission, and we would set this bit to be 1 or 0 depending on the number of ones in the original transmission. If we want an odd number of ones for the transmission, we would add a 0 in this example. The strategic addition of a parity bit in a code can increase the Hamming distance of the code by 1 and enable us to detect and potentially correct more errors. It's important to note that, to the computing system though, the parity bit is an ordinary bit and could also be the bit that gets flipped erroneously. Secondly, adding an extra parity bit doesn't always increase the distance, so you have to do it carefully and strategically. The XOR operation can be thought of as an odd-even detection operation. So if you XOR all input variables together, the XOR will output a 1 if there is an odd number of 1s, and would output a 0 if there is an even number of 1s. This output would signal whether an error occurred. Alternatively, we could use the complement or negative of the XOR operation, the XNOR operation, to flag errors. The XNOR would output a 0 if there is an odd number of 1s, and it would output a 1 if there is an even number of 1s.